All right, so we want to start our next discussion of finding volumes using of solids revolution by finding the volume of this shape right here. So we've got it's not a cylinder, it's like a hollow cylinder. Okay, so you have that kind of thing going, like it's a bushing, or you know, it's like a cross section of a hose, but it is hollow. All right. In fact, what we call this is a shell, cylindrical shell. All right. So let's just talk about finding the volume of this kind of thing. Now, in order to find the volume of this, let's put in some dimensions here. R, it's got a radius of r, it's got a height of h, and then it's got a thickness of you know what? Because we're going to use this, we're just going to call that dx. We could have called it thickness, whatever. All right. But it'll be dx or dy anyway when we get to doing this. So we'll just call that. So those are the three dimensions you need. Now, the trick with this, in order to find the volume of this, is you might think, oh, well, let's find the volume of the cylinder minus the volume of the outside cylinder minus the volume of the inside whole cylinder. And you could certainly do that. However, there's a simpler way. And the simpler way is this. Imagine slicing that right there, cutting it, and laying it out flat. Right? You have to imagine that it's malleable. And we lay it out flat. And when you do that, you actually get a simple shape. You get just this, what we call a parallelepiped, but we'll just call it a rectangular box, right? And that's if you cut it and you lay it out. And so if I want the volume of my shell, I can just find the volume of this box. Now, so how do the dimensions translate? Well, certainly h is the same, and dx is the same. But obviously, radius has, we've lost the radius since it's no longer a circle. But what we need is we need this dimension right here, this measurement right here. But if you think about it, it's simply the radius. Or sorry, the circumference of this area. If we take basically the circumference of that. So the circumference of that circle, of that big circle, is 2 pi r, right? And so the volume of this is the product of the three dimensions. So it's 2 pi r h dx, right? And so that's how we find the volume of a shell, all right? 2 pi r h dx. So we need its radius, we need its height, and we need its thickness. So how does this show up for us? Well, let's imagine taking this function. Here's the graph. This is the function y equals x, or 3x minus x squared, and we've restricted it, so we're only dealing with that portion of it. And let's revolve it around the line y equals x, or y equals minus 1. All right, and so when you rotate it around there, you're going to end up with this shape. So the mirror image is there, and then it rotates, right? Basically like that. Okay? And so you get kind of this upside down bunt cake shape. All right, well, we would like to find the volume that is traced out by this original region, right? So you have to imagine. So basically, this part is hollow, but the rest is solid and it's shaped like this little parabola. Okay, so we're going to play the game we did before, and that is we're going to go over into our region, some distance x. Let's see, let's try this one. Some distance x, and we're going to take a slice. Okay. And in that slice, we're going to, let's do it a little more precisely. We're going to actually just look at a rectangle, not even a slice. We're just going to look at a rectangle, a thin rectangle there. And what we want to do is we want to imagine, how does that rectangle, what shape does that rectangle trace out when it rotates? So that rectangle traces out that shape, a shell. Okay, and so that's why we call this the shell method. So sometimes when you rotate an object, it's better and easier to find the volume using the shell method. And again, you go over a distance x, and you draw a rectangle, a thin rectangle. You imagine what its shape is gonna be, and it will be a shell. And so the question is, can we find the volume of that shell? Well, we need the radius of the shell. The radius of the shell is going to be this distance right here, right? So it is certainly x, because that's x, but then it is also this plus 1, this distance right there. So our radius is x plus 1. Okay. Our height is right there, that height right there. And that, of course, is the function value at x, so that's 3x minus x squared. And then our thickness, because we're doing a vertical rectangle that's parallel to the axis of rotation, is dx, right? And so the volume of this shell, the little bit of volume of our total volume, the dv, is 2 pi times the radius, 2 pi r times times h, times the thickness, 2 pi r h dx. And so that's the volume of that shell. So if I want the volume of the whole thing, I'm going to integrate this thing. Let's see, I started making my cuts at 0, started building my rectangles at 0, stopped at 3. And so it's just going to be the integral 2 pi x plus 1, 3x minus x squared dx. And so setting that up that's the process. You're going to always end up using this procedure right there, that formula to get what you want, right? And then you set it up. Now, a lot of times the shell method is the easiest of the methods, okay? Now, there's some situations where you can't use the shell method, some situations where you can't use the disc method or the washer method. It's all going to depend on the shape and how you rotate it. But in this case, the shell method is nice and neat. This case would be tough to do with the disc method. We'll talk about that here in a second. So let's just finish this one out real quick. So if I want to evaluate this integral, I'm actually going to need to FOIL out expand out all this expression right here. Okay, so let's just take a moment and do that. All right, so assuming we did this correct, we're going to end up with 135 pi over 2, over 6, which of course will reduce down to 45 pi over 2. So we're happy to leave it there as a simple answer, but of course if we needed to know what the actual decimal answer, we would have to plug in pi and figure that out. Now, so there's an example of when we do the rotation and follow that rectangle around, we get a shell, and the shell is easier. This particular example would be really tough to do as a disc method, okay? Let me just show you why real quickly. If I tried to do this using the disc or the washer method, my shape looks like this, right? 1, 2, 3, rotating it around this axis. So 1, 2, 3, or 1, 2, 3, and so this is my shape, right? Roughly like that. Try to keep it simple. So remember, when you do the disc or the washer method, you're making your slice perpendicular to the axis of revolution. All right, so that means we'd have to go up here a distance y and make our slice. Okay, remember, so that's the big thing. You make it perpendicular to the axis of revolution. Now, the thing about this is obviously going to result in a washer, right? A hole here in the middle, something like that. And with the washer, you need the big radius and you need the little radius, right? Well, the big radius would be here. Let's just talk about that. Now, notice the big radius is the outer part of this curve. And that curve is, of course, y equals x minus squared of, sorry, it's 3x minus x squared. And so you would need to solve that for y because it's going to need to be a y measurement, right? Because your integral is going to be in dy because you're making this slice horizontally. So to solve that for y, that's going to be, you can do it. You're going to have to use the quadratic formula, but you would have to do that. And then for the little radius, which is this guy right here, you'd have to do the same thing. And so you're going to get these kind of ugly expressions. And so it might be doable in this case, but it's certainly harder. There are plenty of other examples out there where it is not even doable at all using the washer method. You might look at the result we got up here and say, well, that was pretty complicated. But in reality, it wasn't because it's just a polynomial, and polynomials are easy for us to integrate. We don't have to do anything but use the power rule. So that's an introduction to the shell method.